Hi everyone, this is you are in Ask Teacher J channel, and for today's video, we will be discussing another word problem that will help us understand the topic on first law for closed systems. So this video is actually a continuation of the previous video that I did to discuss a very simple word problem uh, for the purpose of demonstrating the equations uh, or the equation for the first law of thermodynamics for closed systems, which is this one. Okay, let's move on to the second word problem. By the way, the link for the video for the first problem will be posted in the description or in the comment section. Okay, let's proceed to the second problem. So 1 mole of gas initially at 300 Kelvin and 1000 kPa undergoes a change to 350 Kelvin and 500 kPa. Calculate the changes in internal energy and enthalpy for this process. Assume that the gas is ideal and that the heat capacity at constant pressure, which is called the CP, here is 7 over 2 multiplied to R, and the CV, or the heat capacity at constant volume, is 5 over 2 multiplied to R. So the hint for this problem is that we have to, or one of the ways to easily solve the problem is to establish a new thermodynamic path to obtain the required values. Okay. Right. So I took this as I went over my, of course, my personal studying and review. This problem, I really find the problem very interesting since it's a good problem to demonstrate the idea of establishing thermodynamic paths and the idea of using alternative paths to get um, the answer or to determine the internal energy and enthalpy. What is good about, or what is what important insight that you can get from this problem is that internal energy and enthalpy are state functions. As mentioned in the previous video, we have to embrace that idea that they are state functions, and regardless as to what path or the, how do you call this, regardless of the various alternative paths that you might be taking or going over to get the final destination, the value of your internal energy and enthalpy will still be the same because they are path independent thermodynamic functions. Okay, so let's try to demonstrate this. So by the way, I took this problem from the NPTEL or NPTEL Chemical Engineering Thermodynamics lecture series. Okay, so let's start. It would be good to create a schematic diagram for this problem first. So we have here a gas with the following, or the state of the gas is described with the following thermodynamic properties. So let's try it. I'll label this one as state 1. So of course we have N, or the number of moles, to be 1 mole. And then the temperature is 300 Kelvin. And the pressure is 1000 kilopascals. Oh, it's using kilopascals. So I need to be mindful of the value of R here. So by the way, the R here refers to the universal gas constant. Okay, so in the later topics in thermodynamics, you'll be able to appreciate why the value of the CP and CV is for an ideal gas for this particular gas is such because later in my lecture discussion, you might be able to we will be discussing the values of CP and CV for monoatomic and diatomic gases, I guess. So there are various types of gases that follow these values for Cp and Cv, and then there are other gases that follow a different value for Cp and Cv. Okay, by the way, what you need to do for now is just to accept that, okay, these are the values for Cp and Cv, which we will use later. Alright, so for state 1, what we lack is the value for volume. So usually for an ideal gas, it will be very easy to decipher or to solve for the volume because you have this one, right? NTPV. So just to recall the equation for the ideal gas equation, very simple equation that um, high school students know or even elementary students might know. Okay, this is the state 1 for the gas. And the second state of the gas is, okay, let me draw. Okay, the second state still, this is, okay, it's not, we can assume, okay, I think we can state here, I just write it here. You can create your own list of assumptions here. Okay, so for my students, I highly encourage you to create a portion of your solutions that involving your or that present the assumptions for this problem. So of course you have an ideal gas and it was not stated but you can declare. I think it's easy to decipher, okay, but just for your training to properly structure your um, solutions, no, or to establish a framework for your solutions. So declare that the system is an ideal gas and the system is closed. Okay. For state 2 still, you have N of 1 mole and the temperature changed from 300 to 350 Kelvin and the pressure changed from 1000 to 500 kPa. Okay. And you don't have the volume still, right? But you can actually solve for the volumes. So it's very easy to solve. Okay, so we have here the schematic diagram. Alright, so apologies for the poor drawing of the rectangles. So I think we can solve the volume right away. Okay, I think I can solve the volume right away by, we have here PV and RT. Okay, I'll make this quick. V equals, we have here 1 mole and the R here is, this is kPa. I just transform this to uh, 8.314. Oh, oops, I almost forgot the value for R. 8.314 m³ Pascal per mole Kelvin. And then the temperature is 300. Okay. And then the value of your pressure is 1000. Okay. Times 10 to the power of 3. Okay. So let me solve this quickly. Oops. For the value of the volume in state 2, I might just solve it, here directly in the calculator. On your end, if you want to confirm, kindly solve it by yourself. 300 and then 1000 to the power of 3. So you have, okay, 2.4942 times 10 to the power of negative 3. This is meter cube. Okay, for the second volume for state number 2, the value of the volume is, so we have here the same, the temperature is different. So we have here 350 and the pressure is 500. Alright. So this is 5.8198 times 10. So on your end, kindly double check my answers. And then if there are errors, kindly comment in the comment section. Okay, so it's not really that neat looking. Okay, because everything is candid. Okay, apologies for that one. Now, the problem in solving this one is that we notice that there are changes in the temperature. So we cannot decipher that, oh, it's isothermal because there are changes in temperature. So it's not isothermal. And the other problem is that it's not isobaric because if you notice, the pressure changes from 1000 kPa to 500 kPa. So how do we go about this? So it would be good, or I mean, from the lecture discussions that were covered probably by your teacher or by me if I'm your teacher, I have the one of the basics of studying first law for closed systems is there are very common processes or thermodynamic processes done at constant volume and at constant pressure. And these conditions were able to generate thermodynamic relationships between functions or thermodynamic properties. So that is what we're going to employ here. Since we cannot create or we cannot decipher any patterns like there is constant pressure or there is constant temperature in the given, then we ourselves should create or establish that path for us to bring out those thermodynamic equations that are easy to use, and we will be able to get the answers in the determination of the delta U and the delta H. Was it? Okay. So it did not state uh, what type of internal energy and enthalpy is required. It did not state if we need to get the total internal energy or the molar internal energy. So in this case, I will just dictate, okay, since I'm the one solving. I'll just specify that we will be solving for the molar internal energies. Okay? So since we are required to determine the molar internal energies, then we have to report our volumes in terms of molar volumes. So I think what is my mistake here is probably just to write the temperature, the not temperature, the total symbol for this one. But for molar volumes in this case, it's just very easy. Since this is just 1 mole, right? The given is just 1 mole. So you just divide everything by 1 and then just use the same value. But this time, the unit is in terms of moles. Okay? Okay, for this one, the same. Oops, no more superscript symbol. But yeah, the same is true for V2. Okay, going back to the idea of creating a new path, we have to bring out these thermodynamic relationships between the variables so that we can easily determine the overall delta U and delta H for the process starting from state 1 to state 2. So what I mean by that is this. So let's start with step 1. So establish a path. Okay, a path. So I will not write everything, but let's just write S1 for state 1, and then we have here state 2. Okay, but let's write here an intermediate path that will help us bridge state 1 and state 2. So basically, I can just call this state 3. And then for state 1, so we have declared, no, yeah, we have solved already the molar volume. And this time we can apply the idea of a constant volume or a constant pressure process. So we have the liberty, so we are free to declare, because this is the liberty that is given to us. What kind of process should happen to state 1 from state 1 to state 3? As long as one of the thermodynamic properties, either volume or pressure in it, is maintained constant. So if I declare that my state 1 to state 3 is constant pressure, okay, and then if I declare that my state 3 to state 2 is constant volume, okay, keep in mind that whatever values of delta U from 1 to 3, delta U, oh no, delta H 1 to 3, and then if ever I solve again for delta U, or I solve for another values of delta U 3 to 2, and delta H 3 to 2, okay? So remember that whatever path I'm taking, okay, the sum of these values will still be the same. Okay, so I still get the same answer, or if ever, it's just like truncating or cutting the path. So if I sum up the delta U13 and delta U32, I get the same answer of delta U12. So basically, delta U13 and added to delta U12 is, I think I mentioned it wrongly. The sum of delta U13 and delta U32 is equal to the delta U of 12. So that is what we're going to do. Okay? These things are very important. The declaration of the constant pressure and the constant volume are important, because that will help us, or that will force us to use the established equations, okay, that relate the delta U, CV, CP, temperature, and delta H. Okay, so likewise, delta H 1,2 is equal to delta H 1,3 plus delta H 3. Okay, so that holds true. So you might ask, sir, in the first question, you told us that the sum of the loop is for state functions is equal to 0. So let me remind you, or we have to remember that what I'm doing is not a loop, okay? So when you say loop, it should be that the ending, or should be, when you say that there is a thermodynamic loop or a thermodynamic closed path, then that means the arrows should start from 1 to 2, 2 to 3, and 3 to 1. So that should be the loop. But in this case, we are making an alternative path. So I think it would be good to change the color of the path as compared to the color of the original path or the original step. Remember that this is not a loop, okay? It's not a closed loop, but we are creating another path, okay? Because by just focusing on the original path, we cannot determine, because we don't know if this the first path is a mix of changes that will not really help us, or that are difficult to solve. So we cannot use the thermodynamic relationships that we have discussed for first law for closed systems. Okay, so if you ask me, sir, can we interchange constant P and constant V? Can we make it constant V instead and do it here at constant P? The answer is yes. Okay, but at the end of the day, what we are required is the sum of the 1, 3, and 1, 3, and 3, 2 to get the value for 1, 2. Okay, so that's why I told you that you have the liberty or the freedom to establish. So what is the important, or what are the important equations that will bring out that will be useful for solving these alternative paths or steps? Remember in your discussion that for constant V, the equation for um, the equation for the equation that is used has to do with the relationship of temperature, heat capacity at constant volume, and delta U. So this one, the important equation that will be useful for this step is delta U is equal to the integral of CV delta T. So assuming that CV is not a function of temperature, then we can just write that one as delta U equals CV multiplied by the difference of T2 minus T1. Okay. For constant P, the equation that is necessary, or the relevant equation that will help us in solving for the delta H is basically the relationship of the change in enthalpy, the heat capacity at constant pressure, and the temperature. So the integral form of their relationship is this one, and assuming that the Cp is not a function of temperature, so Cp is constant, then your delta H can be equated to Cp multiplied by T2 to T1. Okay. So your question, the next question that you might think is, sir, you have the equation for constant V here, which is only related to delta U, and for constant P, which only involves delta H. What about for the delta H in this side, okay, and for the delta U in this side? This is where the relationship between the internal energy and enthalpy will come in. Remember that the relationship between delta U and delta H is represented mathematically by this equation. Delta H is equal to delta U plus delta PV. So we are going to use that one later. So specifically, the delta PV is just the difference of P2 V2 minus P1 V1. So we are going to use that relationship in a while. So I hope everything's clear. So let's try to number the paths. So we have here path 1 and path 2. So let's solve everything in path 1 first. So let's try our best to solve everything in path 1. So now, for path 1, what we can do, so solve for, in path 1, we have delta U13 and delta H13. Okay, so delta U13 and delta H13. So in path 1. So of course, let's start with delta U13 because that's the easiest one to solve, because we have a relationship here, a mathematical relationship between the variables. So our temperature, this is constant volume. Oops. Yeah, so I think we need to solve something first. So let's try to, okay, I think I need to write everything first. It's kind of time consuming to write, but I have no choice. As a watcher of this video, you also have no choice. So let's, okay, this is, okay, map this one. So we have temperature of 300. Okay. Let me organize everything. I don't like messy solutions. P is 1000 kPa, and your molar volume is... So remember that if I refer to a molar volume, I don't write anything. I don't write the subscript or superscript. The V here stands for the molar volume. So it should have a denominator. The unit should have a per mole basis. So 2.4942. Was I able to read that right? 4942. Okay. Times 10 to the power of negative 3 meter cube per mole. So this is a constant volume process. So you would expect that for a constant volume process, the temperature will change, right? Or even the state. Okay. We have a temperature. This is a known, and the pressure is the volume is 2.4942 times 10 to the power of negative 3 meter cube per mole. Okay. Okay. So for the value of the pressure, so you might wonder, what's the value of the pressure here? Okay, we know that there are changes in the temperature from state 1 to state... Is it state 2? No, it's not state 2, state 3. Okay, what's the pressure here? Remember that in your alternative path, you are expecting that state 3 and state 2 will have a constant pressure. And in the problem, it was stated that the pressure in state 2 is 500, right? So this has a pressure of 500 kPa. So of course, it would make sense to say that, the pressure for this state 3 or intermediate step that we have created should have the same value of P, which is 500 kPa. Okay, so that's what you're going to write here. 500 kPa. Alright. For we have a temperature of 350. So the challenge here is to know what is the value of our temperature in state 3 or in the alternative state 3 that we have created. So it's just very easy to solve. So we have the ideal gas equation, nRT. So for molar volumes, we can just V is equal to establish the equation Vt over N. So we can just write the equation as PV equals RT. Alright, so to solve for the temperature, so we have PV over R. We have 500 Kelvin. 500 kPa rather, apologies. For your volume, that's 2.4942. 2.4942 times 10 to the power of negative 3 meter cube per mole. Alright, and then the R is 8.314 meter cube Pascal mole Kelvin. Okay, we have to take note of the times 10 to the power of 3. Okay, so let me solve 500 times 10 to the power of 3. Then 2.4942. Okay, apologies for the slow solving. You can just fast forward the video if you want. The temperature is 150 Kelvin. Okay, very exact. Alright. So you have a temperature final of 150 Kelvin for this one. So at this point, we can now solve for the value of delta U13. So you have Delta U13, remember that the relationship of, you can get the value of the change in molar internal energy if you have the value of CV and the change in temperature. So CV stands for heat capacity at constant volume. So let's just use T3 minus T1 because we have state 1 to state 3. Okay, our CV, I forgot the value, 5 over 2R. So you have 5 over 2R multiplied by 150K. 150 minus 300. Right. Okay. So our R in this case is 8.312314. So I'm going to use joules, the unit joules per mole Kelvin this time, since um, the joule version is the more useful one. Oops. 150 Kelvin. So the answer is times 8.314 times negative 150. So my answer is negative 3117.75. So please on your end, can you double check to make sure that my answers are correct? If there are mistakes, kindly type in the chat, no, not chat box, comment section. Alright, so yeah, I think I'm done with this one. Now, for the value of delta H13, I think we can solve for the delta H13, given the fact that we have, okay, delta H13 is basically the sum of delta U13 plus delta PV, okay, of 13. So the equation will look like this: delta U13 plus the difference of the products of PV, P3V3 minus P1V1, right? So that's how you write the delta of the products of P and V for state 1 and 2. Okay, so I'm going to write everything negative 3117.75. I'm not gonna write the units anymore since it's kind of annoying. It's kind of space consuming. The pressure is 1000 kPa. I need to be very conscious of the units here. 1000 times 10 to the power 3. Okay, I will be cramping everything. So it should be multiplied as meter cube Pascal. Yeah, that's why I put times 10 to the power 3 here. 2.4942 times 10 to the 3. Okay, I think everything is... Oops! I used a wrong... It should be in P1, P1, oh gosh. Okay, let me delete this. It's kinda tiring to write everything. P3, V3, okay. 500 and then... Okay. So 500... the volume is just the same for both, right? So we can just extract the value of V for both. I think so. Yeah. So we can just do this. V, because V for both state 1 and 3 is the same, and then we have P3 minus P1. That will save us time and space. Okay. So I'm not, if I solve candidly, I might not be able to look for a more efficient way of solving. So please bear with me on that one. 4942 times 10 to the power of negative 3. And then the difference in pressures. 1,500. So that's P2 minus P1. So 500 minus 1,000. And then please do not forget the times 10 to the power of 3 for the sake of the pressure units. Alright, so please give me a few of my... I think I'll just scrap the video. Um, you can solve it on your own. 4942 negative 3. That's the molar volume. And 500 minus 1,000 times 10 to the power of 3. Alright. And then I add it with negative 3117.75. Okay, my answer is negative 4364.85 joules per mole. So I have already considered the meter cube per mole, and then this one is pascals already. Alright, so I have my delta H13. Very simple. Okay. Remember that we can do this alternative path. It's very valid to break the path into small parts and then just add all the enthalpy values for the small paths to get the total enthalpy for the entire process. Okay. Yeah, I'm done. And I'll now proceed to the path number 2. That's U32 and delta H U32 and delta H. Delta U32 and delta H32 for path number 2. Okay, W step 3, delta U32 and delta H32 for path number 2. Alright, so for this one, you have the mathematical relationship. Delta H32 is equal to Cp, and then the difference of this is 2 minus T3. Okay, because the final temperature is in state 2, so that's the T final, and the T initial is in state 3. The Cp value for the word problem is 7 over 2 R. So please take note of that. Delta H32, the Cp is 7 over 2 R. Your T2 is, okay, why am I recalling it? I have it here. 350 Kelvin, and your T3 as mentioned or as solved earlier is 150 Kelvin. 350 Kelvin minus 150 Kelvin. Okay, I think it will be good to expound it in your own paper, but for the sake of making my life faster, I will just write everything here. So I have the value of 5819.8 joules per mole for delta H. Okay, so if you are my student, then I will be requiring you to expound the R and then really show me everything. Okay, and then for the delta U, okay, remember that the relationship is delta H32 is equal to delta U32 plus delta PV432. So let's try to manipulate everything first before we substitute. Okay, so by manipulating through mathematical manipulation, we can get a relationship between U and delta U and delta H to be V2 minus delta PV. This is constant pressure, right? So we can employ some simplifications in the mathematics to make our lives easier. So to continue, so you have the value for delta H32. This can be rewritten as the final is 2, right? So that's P2 V2 minus P3 V3. Okay. So I think we can simplify it further since it has the pressure in this alternative step is constant. So we can just extract it out. So we have P and then that's V2 minus V3. Correct? Yeah, I'm correct. Okay. So let's try to substitute everything. Delta H is 5819.8 minus the product of the pressure that is maintained constant, that is 500 kPa. So remember that it's kPa, so I need to add times 10 to the power of 3. Okay, to make sure that everything is consistent. V2 minus V3. I don't like this part because the molar volumes are not so good looking. 5.8198. 5.8198 times 10 to the negative 3 minus, make sure that you properly encode everything in the calculator, to 2.4942. 2.4. I thought there's something. Oops. That's a blooper in my video. 4942. Alright. Okay. So please give me some time to solve this or to encode this in my calculator. 5.819. Okay, I'm getting old. I'm kind of slow. Alright, but in your exams, I don't want you to be slow. 9.4. Because you're younger than me. So you can solve faster than I am. And then, let's multiply it. Oops. Make sure that it's positive 3, the exponent, and it's negative 3 here. So you might mess that up. Everything will change if there's clerical error. Okay. 5819. Okay, my answer here is 4157 joules per mole. This is the delta U32. Okay, I guess I'm done. Okay, but it took me a long time because I solved everything candidly. So let's now get the values or solve the values for delta U12 and delta H12. Remember that your solve for the required of this problem, or the required values are delta U12 and delta H12. Let's now solve. Delta U12 is the sum of, okay, I'll just sum it right away in the calculator, but you have to show it to me in writing soon. So this is the sum of delta U13 and delta U32. Okay, so let's sum it up. Negative 3117.75 plus, what's that again? Okay, this one. Okay. 4157. Yeah, there's no point typing everything correctly. Okay. We have here 1039.25 joules per mole. And for delta H12, that is Let me sum up. Okay, I'll use this one first. 5819.8 plus negative 4364. So everything is addition, okay? So my answer is, so this is the sum of negative delta H32 and delta H13. My answer is 1454.95 joules per mole. Alright, so I think I'm done with this problem. So yeah, those are our answers for this word problem. Very easy, right? What is not easy here is you not being able to think that, oh, we can create a path. Okay, so it's your learning for this one. It's a very important learning for this word problem. I am free to do what kind of path I want, because regardless of the path, I will, as long as I reach the same state, I will get the same answer for these state functions. That's the main gist of this word problem. Appreciating that delta U and delta H are state functions, and they are not, the value of the answers do not really, or are not affected by whatever alternative path that you are going to take. Okay, so thank you, and I'll see you in my other example videos related to first law for closed systems.